Hello and welcome to Chapter 12. So, this chapter is all about getting an actual game running with server and client-side simulated objects running around the screen. So we're going to primarily focus on putting together both the actor framework itself as well as all of its supporting systems. Another thing I really want to do in this chapter is put together performance counters so that we can track how much bandwidth we're using, how much CPU we're using, and so on, and start to gradually incorporate that information into our design to make sure things are efficient. I want to get that in place as soon as possible, but I want to get the actor framework kind of put together first so we can actually have some fun moving things around on the screen. So what you're looking at right now is where my R&D project is. So this is my R&D branch where I kind of go off and do my own thing. And I wanted to give you guys a tour of it. I wanted to go through what I have implemented as well as the code behind it. I wanted to put in a disclaimer here, however. The code that you're going to see in this video is my R&D code. The final code may be different things. I may decide to move things when we get to actually recording that part, change names, and so on. However, the core concepts are pretty much solid, which is kind of why I'm at the point now where I'm starting to want to put together videos. So, yeah, basically the roadmap for Chapter 12 is we're going to start off with some things like putting together updates for using new Visual Studio, using new Unity, as well as updating some of our libraries. And we're going to have to spend a little bit of time reorganizing some things, like the build system, build order, and dependencies and all that stuff. And we are going to have to make some changes to the way systems currently work. And I'm going to outline some of those changes in this video, and they are very, very much worth it. So I hope you guys will agree at the end here. So first, what I'm going to do here is I'm going to walk you guys through what this project currently does. I mean, it doesn't seem like it does a lot, but hopefully when you guys see the code behind it, you'll understand why this is so important. So first of all, I'm in my loader scene. And I'm going to go ahead and on my game context make sure that our environment's set to development. I have this environment flag where I can connect to my development server or the production server if I want to connect to the production server within Unity for debugging purposes. So let's go ahead and hit play. And what we see here is going to be the login screen. And now the login screen for development purposes shows you a list of all the users. It doesn't require you to log in. Generally on our client, it's a token-based login where the user logs in on the launcher, a token gets generated and passed into Unity, and that uses it to authenticate. So you won't actually see this login screen as a player, but for development, it's invaluable. So we have this list of all these awesome users. Let's go ahead and log in as admin. So let's go ahead and quickly abandon that game. What we see right here is our lobby. We have a chat log, we have our users list, and lobbies list. Not very pretty. I did not spend a whole lot of time on the UI design, but functionally it's pretty much all there. So we have this nice little chat box where we can make chat messages and all that fun stuff. And for the way that we start games is we connect to this master server and we create a lobby. And once we create a lobby, we are now inside this lobby. We can do different things like destroy it or start it. Of course, if I start it, it'll say admin has not selected a player and admin has not selected a team. That's because in this particular game that we're implementing, we are going to they're going to be one-off kind of instance-based games, and each player needs to be part of a particular team and a part of a particular class. Now, I want to point out that the way teams are associated in things like invitations and friend lists and all that stuff, that's all pretty ancillary. And what I mean by that is it's stuff that would be very, very simple to implement within the system as it stands. So I'm not too worried about putting that together. What you're seeing is bare bones functionality. I hope that's fairly clear here. Anyway, so let's go ahead and select a team and a class and hit start. So now you see we are in a game. Now, in this game, it's not that particularly amazing. We have a basic click movement controller using Unity's pathfinding system, which is cool, I guess. And we also have a players list on the left-hand side, and you see admin's the only person there, and he's part of humans. So a couple other interesting things to note about this. We are now connected to a game server. We're no longer connected to the master server. Behind the scenes, there was this handshake sort of deal going on between the master server and the registered game servers, and that resulted in this game being created. Now I'm running on a simulation thread inside of the game server. Now, of course, the game server and the master server are both running on my computer, but because they're different Photon well, they're not different Photon instances, but they're different Photon applications, they could conceivably running on any other machine that you want. So, interesting things. Also, I can hit back. Now, back reconnects me to the master server, and it shoots us all the way back to the beginning of the flow, in this case, the login screen. Again, because I don't have a login token, I see this user list. I can select admin again. Notice how it says you are already in a game, and it'll prevent me from creating a lobby, which is really cool. And then I can hit rejoin, and I'm back in the game. So the game never really ended. It was still simulating in the background. So, like, for example, if I closed out of here and hit Control B to create a client, let's go ahead and do this real fast. I'll pause while it's building. So now I'm going to take the screen resolution. I'm going to put it really low because my screen resolution here is fairly low as well. And then I'll hit play, and I'll go ahead and log in as admin. Now I'll abandon this game. That will result in the game being destroyed from the game server because all of the players have abandoned, because there was only one player anyway. So let's come back here to my other client, and I'm going to log in as an LAQ, and I'll create a lobby. Notice how when I create a lobby appears on the left-hand side. I'll go ahead and select humans and damage. Then over here as admin, I'll join this lobby and select Alethians and support. Now you'll notice that the admin can't start the game because he is not the owner of the lobby. So now I'll start on this side. Notice how our game gets created. So to make this more interesting, I'm going to go ahead and move both the characters next to each other. So I'm going to go ahead and pause the video while I do that. All right, so now they're next to each other, which is pretty cool. So now we can see all the positions getting updated and all that fun stuff. So you'll notice that there is definitely some lag going on here. I did not put a whole lot of time into implementing any sort of movement prediction or lag compensation, but that is something that is going to be implemented. This whole game that you're seeing right here was thrown together in like 4 hours, or probably even less than that. As far as getting from no actor system to having the actor system put together is 4 hours. As far as building the character controller and the movement, what little movement smoothing there is, that took about 30 minutes or less. Which just shows how cool the system is. But there's definitely room for improvement as far as the movement prediction. That's going to be something we'll be addressing. But that's its own issue. That doesn't have to do with what we already have to implement in order to get the system to have the games running in state being synchronized. Now you'll notice if I hit back, and like is still in there, I can jump back in and rejoin, and it's like he never left. So we're able to reattach ourselves to that actor, and that's pretty cool. Now over here, if I abandon, and then I hit yes, I get kicked back to the master server, and notice how that other character disappeared. That actor has been destroyed. Now, the actor wasn't destroyed when I left the game, when I disconnected. The actor was still there. But now he's marked as abandoned, meaning when I hit abandon here, the game is now destroyed. There is no more game thread running on the game's server. Okay, so I also have a lot of logging implemented. So you can kind of watch in real time how things are working. We're going to be spending some time getting the log system set up like you see it on this screen here, with the columns and the different log format and the different colors, because I found this to be incredibly important when debugging this system. So I have a bunch of debug messages left in. I'll probably remove most of these in the future, but you'll see I can see which logger made which message. I can see which game server made each message. Notice how game server 2, it connects to the master server, but then it doesn't do anything else because we connected to game server 1 when we created those games. You also notice I have the master log open as well. Right now we just have a error. This error was caused by me trying to create a lobby when I was already in a game. Probably shouldn't be an exception that's not caught. or it probably should be eaten or just turned into a message because it's a well-known error. And we'll talk about how I do error handling here later on in this video. Okay, so those are our awesome logs. Now let's go ahead and talk about how, partially how I put the system together. So one of my major challenges here with getting everything put together here was making it very easy to work with, design, and change. And the problem with the way I see most multiplayer games and how they're implemented is, in Unity especially, is people like to create a bunch of prefabs and they like to sit there and they configure their prefabs and they have them being instantiated at dynamically. And so there's really no like sort of what you see is what you get kind of editor for how you can manipulate the game or design it or do anything like that. So what I did was I put together a system or kind of a philosophy, I guess, of being able to design most of the game in a what you see is what you get kind of fashion. And this is especially appropriate given Unity's new UI system. So if I open up scenes, you'll notice I have Arena 1, which is the arena game, which you've already seen that. We have game UI, loader, lobby, and login. So let's start off on the login. Now, you'll notice in login, we have our login screen right here, already created. And what's interesting here is I implemented a system that allows you to get or sort of acquire objects when the connection happens. That was a horribly contrived sentence. So let me show you guys. Login system. So you guys remember systems, right? So systems are basically the bi-directional communication between a server and client. You have things like a login system or a lobby system or maybe even a character select screen system. And what I was able to do was I was really, really tired of systems being instantiated dynamically at runtime. And the issue I had with that is I wasn't able to take advantage of hooking up objects that exist in a scene into that system's properties. So what I did was I made systems able to be added to the scene, any scene that you want, and when that scene loads, when that system gets instantiated server-side, what it does is it hooks into that instantiated object. So this login system can be configured here inside of the Unity editor, but when we're connected to the network, it will automatically attach itself to that context. Meaning we can sit here and give things like the users list or the user and list button, which is a prefab that gets instantiated for each item. And then we also have our debug window, which is the whole window. For example, in the login system, if we have a token available, so for logging in through the launcher, it'll hide this window. So anyway, now what happens if you hit play? Now, another part of my philosophy that I've developed is that if you open a scene and you get a WYSIWYG editor, if you hit play, you will get an instant ability to test that piece of the code or that design or anything like that. No network connection, no waiting for anything. Just hit play and test your stuff. Really emphasizing a very tight feedback loop. So any sort of minor adjustment you make to either the system itself or to what you see on the screen, such as the UI, you can test instantly. So I can go ahead and hit play and we get login. Now, you'll notice that this player list actually looks different than the player list we saw before. That's because what I'm doing here is I'm detecting that we're not connected to the server. And so when the login system gets instantiated, he instantiates a special server test system that's written on the client side that kind of mimics a server and does servery type things. We'll take a look at what that code looks like here a little bit later. But the point is I can now sit here and test this locally without a network connection or a connection to my server, without waiting for latency or database connections or anything like that, and get a very tight feedback loop and be reasonably certain that when I actually launch this for real against an actual connection, it'll behave in the same way. So not surprisingly, I have the same sort of thing done with my lobby. So the entire lobby is created from the new UI, and it's all created in this WYSIWYG editor with as few prefabs as possible. Because I used to, on my first iteration of this, I had all of these panels or these windows be prefabs. But then when I try to manipulate those prefabs by like removing a child element from it or adding a child element for it or whatever, it would break the prefab instance, and that just got really tiring. So the only things that are prefabs here are these guys right here. The individual list items, which are prefabs that you can manipulate here, and what you see is what you get fashion. But when you hit play, they'll be removed. So you can see everything right here. Right here, you see on this screen, we have our lobby list window or lobby details window. I can show or hide these depending on which one I'm working on at the time, and the system itself will automatically show and hide the correct one. So I can leave this in whatever state I want, and the system, when it connects to the server, will show and hide and move around things that it needs to. So now if I hit play, you'll see that we have a fake lobby system, including a fake chat. And we can also create a fake lobby. And our fake lobbies, you'll notice, have fake players. And when we try to change something, you'll notice that we get fake latency. So you can really go ahead and you can test and build all these things the way you want to within an editor. A designer could do this for you, a person who doesn't know anything about code, and they get the tools they need to rapidly develop these. Now, again, I've been referring to this as a philosophy because in order to make systems work like this requires discipline. So, for example, not using static objects or any of the other, poor what people know as anti-patterns or poor development practices. They're no longer optional when working like this. You really need to have a very test-oriented sort of modular sort of perspective in order to make systems that work like this. But it pays off. And here's an example of those best practices paying off. So again, if you guys have ever worked on a multiplayer game before, having to every time you want to test one little aspect of the UI, having to log into the server, type in your username, password, go through the lobby, blah, 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 10 clicks just to get to that one thing you wanted to take a 2-second look at, you no longer have to do. Okay, so now that we're going through our project, our scenes here, let's look at the game UI. So the game UI is, not surprisingly, the game UI. So here are our abandoned back buttons and our players. So the way this hooks in is we have this main menu window, which is a single instance object or something like that. It's basically a object that can get accessed from a system. And so it gets automatically attached to that context when it gets created. So here we have our main menu and our players, and we even have our separator prefab and our player and item row prefab. Again, you can edit these with the WYSIWYG editor, and they'll be removed when you hit play. So this game UI is loaded additively to the arena or whichever arena that you choose to whichever scene that has the actual game in it. It's added to that. So here's the Arena 1, which the Arena 1 isn't too exciting. It's just a map I put together in 2 minutes. And again, not that amazing. However, there is one cool thing about this. Now, the thing with this game is there will be a way, eventually I want there to be a way where I can test things like player controllers and particle effects and all that stuff without connecting to the server. But in this particular case, I wanted to see how easy it would be for me to put together a way for me to hit play and actually create an actual game on the server to test with. So I have this game object here called Start Game. And what Start Game does is it bypasses the master server completely and signs you in to a particular server and a particular application name with a particular user ID. And does that automatically and creates the game and starts everything for you. So if I hit play, we get an actual game. So I'm in an actual game that's being simulated on an actual server. In fact, if I were to hit back and log back in as admin, well, it didn't get the memo apparently, but it should. Oh, right. Never mind. My start on game object, when you do on application quit, it'll automatically destroy the game. So that's why there was no rejoin button. Anyway, so that's just a quick tour of how I've set things up, how I want to really encourage tight feedback cycles. Really the only thing I can't show you guys here, which I want to implement, is a way to create the player controller and other things so I can test, like I said, particle effects and the game UI without having to actually create a physical game. But this is really great when you're working on server-side code, because all you have to do is change your server-side code, hit play, and now we can come in here and test an actual real game without having to go through a lobby. Okay, so that's that bit. So yeah, there's a couple other really interesting things I put together, such as under resources prefabs. I have this prefab instantiation system for things like alert dialogues, confirm dialogues, and actors, in this case player avatar, which is fun stuff. We'll see examples of this when I walk you guys through the code. So let's just really quickly walk through the code, show you guys how these things were implemented. Or not necessarily how the infrastructure looks, but how the end code will look. So let's start off with... let's see here. Let's start off with the client. We can really quickly walk through my systems.master. So here's our login system, pretty straightforward. You'll see right here I have a conditional if statement. If it's a development build or if it's the Unity editor, then log in with the user select. Otherwise, log in with token. Token being the thing that's passed in from the launcher. So if we log in from user select, we simply set debug window.setActive. So remember, that was that window that was available in the scene. Now remember, this login system is already instantiated by Unity when the login system, or when the login scene gets created. So this is this game object right here, this login system, which has references to other game objects in the scene. So I can take advantage of these references just automatically, and I think that's really cool. It makes things very... it reduces a lot of code, basically. So then we have things like set available players. So set available players is a method that's called on the iLogin system client. So this is actually sent in from the server. We loop through all the users and we add buttons to the list. And then we add a listener to each of the buttons saying, when you click on the button, do the login with proxy.debug login. So here's a little bit of an interesting foreshadowing to some of the things that I'm going to be other things I'm going to be talking about in this video. Look at this code carefully. So we say add listener, we invoke do login. And if you look at the signature of do login, it accepts a deferred of user details. So what is a deferred? All right, guys, you remember IRPC method and RPC response and in-process RPC response and deferred RPC response and that madness of a class hierarchy? Well, it's gone and it's replaced by one class. Well, technically two, but the other one you don't really need to use directly very often. Basically, deferred, we'll see more examples of this in the future, and in fact, I believe in the next video is when we're going to be building it because it's very important. It allows you to encapsulate asynchronous requests. So, do login invokes proxy.debug login. If I look at the definition for proxy.debug login, it's in the iLogin system server. Well, actually, it might be more appropriate if I open that up on the server project. iLogin system server. So you'll notice on iLogin system server, these methods return a deferred. In this case, it's deferred of user details. In this case, a deferred of nothing. And that replaces IRPC method. So debug login returns a deferred, which gets passed into do login. Then do login says callback dot on success, do something, on fail, do another thing, and then on always, do a third thing. So it really looks like IRPC method right now from this perspective, but when we look at the implementation and the other really fun stuff we can do with deferred, then I think it'll become more apparent why I chose to put this implementation together. Anyway, so do login simply happens, it accepts a deferred of user details, which can come from either performing a debug login, as you see here on line 43, or performing a login with token, as you see with line 28. So in either case, the same method, do login, gets invoked. And in this case, what it does is it says status equals context.prefabs.status message. So context is the global object. We've already talked about what the game object is. It's kind of the main coordinator of the entire system. Now prefabs is interesting. Prefabs is a prefab factory. And this was what I was talking about earlier with being able to load in prefabs. But what the prefab factory allows you to do is it allows you to put prefabs inside of your... let's go ahead and jump into my garbage scene. So here's an example of my confirm dialog, and this is the prefab of the confirm dialog, and you'll notice it has a very special component attached to it. It has a confirm dialog script attached to it, which has references to all the bits that that script needs to deal with. Actually, let me go ahead and I'm going to remove the confirm dialog, and just because we're looking at the status message dialog right now, we're going to focus on that first. So, the status message is an alert dialog. So here's our status message dialog, and you'll notice it has a class of type alert, or a script of type alert dialog. Now, there's two important things about this prefab. A, it's located under the resources prefabs folder. That's important. B, the script alert dialog, if we load that up, inherits from a thing called prefab behavior. Those two things combined basically allows my prefab factory to locate it and register it with a bunch of types. So now what I can do is in my login system, if I want to display a status message, I can say context.prefabs.instantiate alert dialog, and then I can say .set title, and then how about .close, close in 2 seconds. So this code right here instantiates the alert dialog. It knows what prefab is associated with that because that prefab was added to the resources prefabs folder and loaded in. And then we can configure it using a very simple fluent syntax here. So the status message method basically just does that. It does literally what I just showed you guys. The status message is a helper function or method on the prefab factory, which takes in a string message, instantiates an alert dialog, sets the message, and sets can dismiss to false. So the dismiss button doesn't appear. Anyway, so we create the status message, and then we always close it no matter what happened. However, if we failed, then we alert can't log in with the operation error. And if we do success, then we do context.authenticate details. So on this deferred of user details will return user details as an object when we authenticate. Then it says context.loadLevel on success on level loaded. So this is cool. This is another example of a deferred, but a deferred that has nothing to do with the network connection. So my context.loadLevel method, what this does is it simply loads the level. So it starts a coroutine, load level co. It instantiates a deferred first of all, then returns that deferred. Then load level coroutine loads in the level, and then after it's done, it yield returns load level async, which used to be a Unity Pro feature, but now is a Unity free feature. And it'll wait until the level's loaded, and then when it's done, it'll set the result of the deferred, which will in return invoke the onSuccess method of that deferred. And in this case, we have onSuccess to onLevel loaded. So this is a really compact way to say load level lobby, and when you're done, do this other thing. So again, the biggest reason why I removed IRPC method was because it was only really appropriate for server-client communication, but now the deferred API is so much more abstracted out of that, you can use it practically anywhere. So now onLevel loaded, what we do is we say proxy.join main lobby, and then we only handle the failure. So remember, at this point on level loaded, we are in the lobby level. So then we tell the server we're done loading the level now, so join us into the main lobby. But if it fails, tell the user why it failed, and then load level login. So go back to the login screen. So it's a two-step process, or a three-step process. A, login, B, load the lobby scene, and then finally join the lobby. Anyway, that was a lot more detail than I was expecting to go through on this particular system. But there you go. I mean, this is basically all the code you need for the login system for the client. It's very short and compact, takes advantage of a lot of the things that I've been spending a lot of time to put together. So let's look at the server tests. So remember how when you just hit the play button, any system that's instantiated will connect to a fake server in process? Well, the way that works is I have this object called entry point, and the entry point object is only on the loader. And it's right here, entry point. And if the entry point object is instantiated, the system assumes that it's connected to a server. If it's not instantiated, it knows that it's not connected to a server, so when the login system gets instantiated, when we play it, it will find the corresponding server test. An important thing to note, all of this server test code is blocked in with a Unity editor or development build, and that means that this code's never going to get compiled into a production build. So you're safe to put whatever you want inside of these system tests. In addition to that, you can't forget to throw in these conditionals because the Unity system test base itself is wrapped in these conditionals. So if I forgot to put in these conditionals, I try to do a production build, the build would fail. So you don't have to worry about accidentally putting, confidential information in here. But anyway, this login system server test is basically the exact same thing as what the login system would be on the server, except it's fake. So you notice on ready, I say proxy.setAvailablePlayers. Now what is proxy here? Let's hover over it. It's iLogin system client. This proxy object is literally this login system. So there's no sort of delay or intercept or anything like that. It's literally that other object. And vice versa is true. When we're in a debug mode, this proxy object is literally this object right here. So we set available players, and we have a login. I didn't implement this login because in a development build we'll never receive a token login. But on this debug login, we simply say if user ID is 1, return deferred success with these details. Otherwise, return failure. Then we have join main lobby, which simply creates the main lobby system, disposes ourselves, and returns success. So really simple, not a lot of code, but allows you to test all of your components. All right, so I probably won't go through this too much. This is the main lobby system, pretty straightforward, just more of the same of what you saw. More examples of how deferred is awesome, stuff like that. Not too exciting. The lobby system is a little bit more interesting. The lobby system is important because it's responsible for joining a game. So when we receive the onGameStarted message from the server, we say context.joinGame and we pass in the game connection details. So onGameStarted is going to tell us the game ID that we're connecting to, the name of the level we need to load, and the server that we need to connect to. Then we invoke the gameContext.joinGame method. And the joinGame method does a couple interesting things. First of all, it disconnects us from the master server. Then it does something really cool that uses our deferred implementation. It says return connect to server, and connect to server, not surprisingly, returns a deferred. So you'll notice connect to server checks to make sure we're not already connected to a server, disconnects it if we are. Then we do onConnect equals new deferred game server system, and then we instantiate a game server module, passing in our onConnected deferred. So this onConnected deferred will be resolved once the game server connection is established. So that means this logic right here, how we join a game, reads like this. We connect to the game server, then we get the server system, and we tell the server system to join our particular game. And then if we fail, we tell the user we failed and we return to the lobby. Look at this then. We're going to be talking a whole lot about then, or maybe not a whole lot, but a bit about then in the next video when we build our deferred implementation. So then is, what it does is it accepts a function that returns another deferred. So basically, connect to game server and server system.joinGame, these two deferreds got combined into one. So it'll only set the final result when both of these things are done in sequence. That's another important thing. It happens in sequence because we need the return object of the connect to game server in order to join the game. So let's look at join game. It uses another instance of then. So we say context.loadLevel. You remember load level, right? We put together the, we load the level and we wait for it to finish. Then once the level is loaded, load the game UI, but additively, right? Then finally, at the end of that, join the game. So we have this huge chain of asynchronous logic happening right here. And it's implemented in very, very, very few lines of code. No callbacks at all. Well, there technically are callbacks, but no callbacks as in creating different methods, registering new operations, blah, blah, blah. All you have is a single chain of deferredness. So at the end of the day, this join game deferred, will only finish after we where are you? We connect to the game server. B, we now we do join game, which is another composite deferred. We load the level. C, we load the level UI. And finally, we tell the proxy, we tell the server that we're all loaded, ready to go, ready to start receiving actors. And then if any of that fails, because this on fails at the end of the chain, if any of that fails, then we have this operation here, this error joining game. So it's super powerful because, like, for example, if I had another thing I wanted to add here, another step, I guess you could say that's asynchronous, I could do so. Anyway, I know I'm gushing about the deferred thing a lot here, but honestly, it's worked out incredibly well for implementing this logic. Anyway, that's pretty much all I want to say about the client for now. Let's look at the actor system. So the actor system is the most important thing. It's mainly what we're going to be focusing on throughout this chapter after we build the way that, or after we build the basic load balancing. So, well, we can look at that, I guess, a little bit right now, the load balancing. So in our master, we have our login system, our main lobby system, and our game main lobby system. So in the login system, pretty straightforward, not very much code. All it does is checks the user's either token or username and either token or ID against the database. And if it does, it logs in on the context. Context.login just sets that the context is logged into that particular user. And then we notice that we can return deferred.success if the method is not asynchronous. So if the method is synchronous, it can simply return deferred.success and that method is done. However, join main lobby is more interesting because join main lobby invokes main lobby service.addPlayer, passing in our player context. And then if it succeeds, then we destroy ourselves. We destroy the login system. Login system is no longer required once we're part of the lobby. So here's an example of us using more deferred stuff. So in the main lobby system.addPlayer, the main lobby service is responsible for kind of synchronizing all the main lobby stuff, like chat messages and stuff like that. And what's really cool about it is the main lobby service has this system proxy.imainlobby client. So imainlobby client is a system proxy defined in our BuzzMMO based component system. So this is the interface that our client system implements. But what I did is I created a system in which I can broadcast a proxy invocation to every single or to a list of users. So in this case, you'll notice that we create this proxy, and this proxy is of this type, but we pass in this selector right here that selects out all of our players that are currently in the lobby. So now anytime I invoke proxy.whatever, this method is invoked on every single client that's in the lobby. So no for each loop, nothing like that. Just if you want a message sent to everyone, you just do proxy.whatever. So add player is really simple, and it points out something really cool about the deferred system. Most of the code here is error handling. So we make sure that the user's not already part of a system. We make sure they're authenticated. And notice what I'm doing here. I'm throwing a new RPC exception. So the way I deal with errors in this code is I throw what I call an RPC exception. An RPC exception is recognized by my code as being a message that needs to be sent back to the client. So most exceptions are not sent back, or all but RPC exceptions are not sent back to the client, because that would be a security risk. We don't want the client knowing anything about the internal errors that we may or may not have. RPC exceptions, however, are different. They get returned back to the client. So that's how we can handle sort of verification and other sort of things in a really, really clean sort of way, using exceptions as they were intended to be used. So at any point, if I throw a new RPC exception, the deferred is considered failed. So onFail will be invoked on the client. Now look at this. So this returns a deferred, and we have a fiber. If you're not familiar, in Photon, we have these things called fibers, and they're used to synchronize our code. So only one action can be running on a single fiber at the same time, so we don't have to do any locking inside of this code to worry about multi-threading. Now, enQDeferred is an extension method that I wrote that wraps the enQ method of the fiber with a deferred. The logic is very simple. We enQ the action. Well, first of all, we instantiate a deferred, and then we return that deferred. Then inside, we queue the action to the fiber. We try to run it. If we succeed, we set the result to valid. If we catch an RPC exception, we set the result to failed with the RPC exception message. If we catch anything else, then we say there was a fatal error. And then, most importantly, we rethrow the error. So by rethrowing the error, we'll get a stack trace in our logs, but the error won't be set back to the client. So anyway, back to the main lobby service. Again, the service responsible for kind of being the room of the chat room of where all the clients are. We return enQDeferred. So this deferred will succeed if it gets to the end of this method without throwing an exception. We do some error handling. We instantiate the main lobby system. We tell the player about all of the existing players in the lobby and all of the existing lobbies in the lobby. Then, on this one line of code, we tell every other player that this player has entered, and then we finally add that player to our data structure. Pretty straightforward. So I'm not going to go through the rest of these methods. They do what they say on the tin. Remove player is just the opposite of add player. Create lobby, well, not surprisingly, creates a lobby, and so on and so on. Now you'll notice that on all of these, I say all the deferred ones, I say fiber.enQDeferred. Oh, this is a fun one. So what about a deferred that returns an object? So this is a deferred of GUID. So lobby IDs are GUIDs. And how do we return that object? Well, inside of enQDeferred, I created another overload that we can just write a return statement. Like, it literally couldn't be any easier to write more asynchronous code, with the exception of if we were using async await and the TPL in C#. So this was the best I could do. But it works out really well. It makes the code look really clean. Anyway, so that's our main lobby service. If we open up our game lobby service and begin game is a bit of a pain. Oh, and you'll notice that you'll see one of my rare comments right there, just because it looks kind of weird what I did right there, but it actually makes sense if you read the comment. This is really fun. So this is an example of how the deferred system is able to chain really, really, really long-running complex operations. So when we begin the game on a lobby, we first make sure that the lobby is active and that it's valid. Then we create the game parameters. The game parameters are what's set to the game server to instantiate the game. So for example, things like what map to play, or what game type, or what's the time limit, stuff like that. Then we say return game servers.begin game parameters. Now, on success, we will receive game info, which is a game server context.gameinfo. And if we do that, what we do is we say fiber.enQ, and we tell every single player that the game has started. And if we fail, we tell every single player that the game has failed. Then at the end of this, we replace the return value with a empty deferred.success. That'll make sense in the next video. So begin game has a lot of things to do. So begin game enQs deferred on its own fiber. It then selects a game server. Once it selects a game server, it tells the game server to begin the game. So we're now 3 deferreds deep. Inside of begin game, we create a deferred of game info, and we do fiber.enQ. We don't do fiber.enQ deferred, and the reason is this deferred is only going to be set to valid once the game server has acknowledged that it's created the game loop. So this deferred has to stick around for a while until finally everything is finished and the game server has told us that it's ready. So the first thing we do is we create a game waiting to start. We then tell the game server that we want to start this game, and then we add that game information to our games waiting to start. If at any point there is an exception, we reject the deferred, which again, this deferred.setResultFalse will bubble all the way up back into the client. So without having to write any additional code, in fact, begin game doesn't care that it's being invoked from a client or another server or a batch script or anything. But when it sets its result, that result will bubble up to whoever called it without this object knowing anything about who called it. So anyway, games waiting to start is just a list of games that, well, are waiting to start, actually. But what it's used for is, what happens is when we get an on-operation request from the game server, if we get a game started, we do our games waiting to start, we get it from the token, and then we finally set the deferred's result to valid with the game info. So, basically, all the way over here, when this gets set to valid, it will bubble all the way back to the client and all the clients in the lobby to tell them that the game has actually started. If the game failed to start, we do the opposite. We set the deferred's result to false. Now, another interesting thing is for the games waiting to start, I also have a check for dead games method that's invoked every once periodically, and it'll check to make sure that the game's waiting to start. If it's past the dead game delay, it'll go ahead and automatically set that game started to false and invoke and say that to the clients that the game couldn't start. So we have to put this logic in here in case there was an exception or an error somewhere on the game server so that our stuff doesn't get very cluttered and that the client eventually gets notified that the game's not going to happen. Well, anyway, I hope you guys are having fun. I really just wanted to show you guys the systems, what I've put together, what you guys have to look forward to. Again, names are subject to change, but I already said that. So, all right, we've talked a lot about deferred. We've talked a lot about the master server. Let's go ahead and jump into the game server. So the game server is still called server.region, which I know it's now more of a game server, not a region server, but whatever, I'm not changing the name. A couple interesting things. We have config. I'm going to find a better way to do this configuration. I'm being kind of lazy right now, and I just have all of my debug servers and all of my production servers configuration listed right here. Again, super lazy, but I'll figure out something better in the future. It's not that hard to change. So for example, my game1.debug.json creates a game server. It says where it can be reached at from a UDP connection, what its application name is, its name, and then its unique ID. Every game server has a unique ID, and the reason for that is that these game servers are stored in the database, and so they need a way to associate with a GUID. Anyway, so this is our region server. Our application, so remember, the application is Photon's entry point. This object is instantiated when Photon starts this particular game server. It reads and configs, it starts its fiber, blah, blah, blah. But most importantly, it connects to the master server. So most of what this class does is it connects to the master server and tells it, hey guy, I'm here and here are my connection parameters. So now the master server knows about this server. So that's super exciting. What else? So the game server context. This is a really important class. This class is responsible for managing, this is kind of the entry point for all the individual games that are on the server. So it has things like kill orphaned games, which is responsible for looking at the database, seeing, hey, the database says this game is going, but actually it's not, and then it kills it in the database. It also does things like begin game. It does things like join game, where again, we have a lot of error handling, but it's necessary. We want to make sure that the user is supposed to be in the game. We want to make sure the user is not abandoned. We want to make sure the user is, the game is not destroyed, and so on and so on. And then we have abandoned game, which does this similar thing, and so on and so on. So not too interesting. You can think of this class as kind of the entry point for all of our game instances. Now, a game instance is basically, think of this as a wrapper around the game engine. The game instance is responsible for dealing with players entering and exiting. Basically, it's the gatekeeper to the game engine. And you can see the game engine gets instantiated right here inside the constructor, as well as our game thread. So we create a thread and we create a game engine. We can add a player, and adding a player, again, does a lot of stuff. This is the gatekeeper for the game instance. When we add a player, we have to do a lot of validation to make sure that player is really, really supposed to be in that game, because if he's not, we gotta boot him. And again, I make a lot of use of deferred. So, for example, game engine.add listener, and so on and so on. So we have an abandoned game. Again, a lot of validation. The logic is actually super straightforward, I promise you guys. I know it looks like a lot of code, but most of this is validation. And abandoned internal. So this is the code that's ran when everything, a player finally for real abandons. You'll notice that if player, this is where we destroy the game. If player count equals 0, then abort the game. On player disconnected. Super straightforward. Now, the most important method in this entire game instance is this one-liner. Run game, which simply says game engine.run. So, an important thing about this is run game is going to be invoked on a different thread. So all the games run on their own thread. And then in here, we have game engine.run. And game engine.run, well, let's look at game engine as a whole now, instead of looking at that. So the game engine, some things about this are subject to change. This is one of the newest classes that I've added to this. But the game engine is just like what it says. It's the engine, it's the game loop. It what runs the actual game logic. And there's a couple important concepts to understand about it. For example, we have a list of transports. The list of transports is basically the list of all of the connected things to this game engine. All of the things that this game engine needs to tell about when something in the game changes. So it could be anything from a player to maybe a dashboard system or an automated script or something like that. Anything that needs to be attached to the game and listen to the game is considered a transport. We also have actors. So actors are basically what is in the game engine that does things. The individual entities. For example, your creeps, your towers, your NPCs, and so on and so on. It could also be more abstract things, like maybe we would want to create an actor, a game spawn actor, for example, to block off where players are supposed to spawn. So that's our list of our actors, and so on. So inside of this, we have this queue action method. Queue action is important. It's basically, I implemented my own concept of a fiber with this game engine. And queue action, what it does is, if we are whoops, this is backwards. If we are not in this thread, then queue it in our action queue, otherwise invoke the action directly. So this is used for anything that needs to interact with the state of the game. Everything is synchronized on a single thread. That's very important. Actually, writing a game like this with multi-threaded code is going to be practically impossible. I guarantee you that's not something you want to do. So everything is synchronized on a single thread. When I'm in an actor's method, that is in its own thread. Or not in its own thread, but in the game loop thread. We have this create proxy for. We'll talk about that a little bit later when we talk about actors. We have add listener. Add listener is obviously used to attach a listener. So if a player joins, we add him as a listener. Now you notice something interesting right here. When we add the listener, what we do is we queue an action first, but then we serialize the entire state of the game. So we loop through all of the actors and we tell each actor to write its full state out into a memory stream. And then when it's all done, we send it to that transport. All right, so then we have remove listener, which does what add listener does, but in reverse. Then we have add actor. We'll talk about that later. And then we have run. So run, basically, just runs the game loop. So while we're running, we do some things. First of all, we dequeue up to max action count actions. So we dequeue up to 5 actions per loop iteration. That's an important optimization thing. I don't want to run too much in a single tick. Also, you'll notice I do a lot of error handling here. That's important because any exception that's not caught here is going to kill the thread, kill the game, and we don't want that to happen. So we need to make sure that we eat all of these exceptions. Otherwise, it'll be bad. Then next up, we'll talk about this in a second. Then what we do is we say send state in minus equals elapsed milliseconds. So what this means is every X amount of time, in this case 100 milliseconds, we send out the incremental state of every actor. So every actor has kind of 2 states. It has its full state, which contains all the data about it, and then it has its incremental state. This incremental state contains only the properties that can change throughout the course of the game. So then we do a update. Now, update is an abstract method that can be overridden on any class that subclasses game engine. Then we loop through all of our updatables. An updatable is an actor with a particular interface on it. And so not all actors are going to receive the update tick, but the ones that want to can implement the interface iUpdatable, and it will receive this update. Then at the end of this, we calculate how long we have to wait in order to how long we have to wait until the next tick in order to get a particular tick per second. And then we sleep for that amount of time. And if we can't, then we do on slow tick, which on slow tick is going to notify an event that our game engine is actually taking more time to run a tick than it's wanting to meet its particular tick per second parameter. So this is for debugging purposes. Okay, let's talk about actors. So, actors are, I've already described what they are, but they're inside here, inside primarily this one actor class. And this class takes in a generic type parameter tproxy. Now, tproxy references a actor component. So if I scroll up to my buzzmmo.base, in components, we have an actor's namespace now. In this case, we have one single actor, in this case, iPlayerAvatar, with a setHealth method. It's not used in the current game, though. Now, what this actor does is when he's instantiated, he gets a game engine, and then he creates the proxy for that particular actor component. Now, what's really cool about engine.createProxy4, and this is really cool, it's going to send all of any of the methods invoked on it to every single transport that's connected to the game engine. So we can create proxy 4, and every time we invoke any method on this proxy, it's automatically sent to all of the clients. So then we have some basic movement code and some concept about state. So again, we have if not send full state, which is used for things like on the first actor's tick, it'll send its full state. So when the actor is created, it'll send out its full state if it needs to, and so on and so on. And then we have our write incremental state, which writes its ID, its position, its rotation. We also have we have actor type. So what's interesting about the write full state is how a client knows what actor to instantiate on its side. So when an actor is created on the server, the client is going to receive the state information, but it needs to know what kind of actor it is. I mean, is it an avatar? Is it a creep? Is it a tower? What is it? So we have this actor type.id. Now, actor type is going to be the mapped component. See if I hover over this? The mapped component of the proxy type. So it's going to be the mapped component, in this case, of iPlayerAvatar. So that's how the client is going to know that this is an avatar or something else, depending on what proxy we passed in. So anyway, that's it for the actor. Pretty straightforward. Here's an example actor. We only have one so far, player actor. So player avatar inherits from actor of iPlayerAvatar. Again, that's how the client knows what to instantiate. it accepts a CTF game engine. It has a player ID, team, hero, health, max health. Now you'll notice that inside of our well, first of all, you notice when it's instantiated, it moves itself to engine.getPlayerSpawn location. So it moves itself to wherever the engine wants to spawn it. Then we have write additional full state, which sends out its player ID, its max health, and its health. So this is how the full state is how the client knows what player ID it represents, what's its max health, and what's its health, and so on. I'm not going to be doing anything fancy with serialization with this, I don't think. The full state and the incremental state need to be super fast and super compact, so I'm most likely going to just use binary writers and binary readers. That might change in the future, but right now, that's how I'm going to be handling state. Okay, so next up, let's look at the CTF game engine. CTF game engine subclass is game engine, and it has its own update method, which is empty, and it has its get player spawn location. Nothing crazy, but this is where you would put the overarching game logic into this game. You would put in, once this flag is captured, do this, blah, blah, blah. That would go into this game object. Alrighty, I hope that you guys are getting a feel for how this works. This turned out to be a lot more to talk about than I had originally anticipated. I was originally anticipating this video to be like 10 minutes, but I guess that's what I always say. So let's go ahead and continue with a couple more things. I'll try to be quick. Let's talk about how the player avatar is even created, because that's really important. So inside of our systems, we get our game server system. And our game server system has this join game method. So when the client says, okay, I'm ready, I've loaded my game UI, I've loaded my game level, I have all my information, I'm ready to join the game, it invokes join game, which returns join game, as a deferred. So inside of this join game, what happens is if the game exists, we return game.addPlayer. Now inside addPlayer, what we do is in queue deferred, we do a lot more validation, because of course we do. Then we get the player parameters. We create the game system on the player. We then tell the player about all of the other players that are currently registered with the game. We then tell all the other players that this player joined. Then we return GameEngine.addListener. Context transport. So right here, inside this method is where the game engine is going to tell the client about all of the actor's state. Then on success, so when it's done, we create our player avatar. Actually what we do is we keep track of all the avatars that are created so we can reattach avatars as needed. So if the avatar has not already been created, then we instantiate the player avatar. Now remember, this is an actor. Passing in the game engine, the user ID, the team, the hero. We add it as an actor, and then we add it to our avatars list. Then next up, we do system.init this avatar. So system.init is on the game system, and it tells, and it's responsible for allowing the player to control the game in different ways. For example, abandon. Position update is actually not handled there, so I should delete that code because that gets confusing. But right now, the only game-wide thing you can do or act on a game is abandoning it, and that's about it. I can imagine other things here being chat, for example, doing in-game chat, and other things like that. And there'll be other game systems for things like classes and leveling up and sending abilities and stuff like that. All right, so before we look at how the client deals with actors, let's look really quickly at our, where was I looking for? Region player context. Oh, right, I did use that method. Why did I delete that method? You guys didn't see that. Okay, inside the region player context, we override the on operation request. And we say if code equals position update, then tell the game to position update. And then this tells the avatar to move, and then the avatar gets set as dirty. So pretty straightforward flow, but the reason I'm doing it here and not in a system is for performance. Now, things like leveling up or sending a chat message or anything like that, they happen so infrequently relative to CPU clock cycles that I don't care about the performance overhead of using our systems to do that, using our bidirectional proxies. In the case of position updates, though, that is sent so often, so frequently, that I really want this code to be as optimized as possible. In fact, there's further optimizations I can do for it, like, for example, only sending 4 bytes to represent a position delta instead of sending 12 bytes. But, again, I implemented this really quickly on a Friday afternoon, so don't hate me. Once we have performance counters in place, we can start monitoring bandwidth usage. We'll definitely come in and start tweaking how this stuff works. Okay. So, now let's look at the client code real fast, then we'll wrap up. So in the client code, how do actors get created? So actors get created primarily through the use of the game server module. So the game server module, think of it as the connection to the game server. This is the entry point to the individual game server. This is the class object that does the connection, receives status updates, and all that stuff. So if we scroll down here, we for event registrations, we register a send state, a destroy actor, and a invoke method on actor. So send state invokes on state received. On state received simply loops, checks to see if this is a full state or a not full state. If it's a full state, it loops through every single actor, it loops through the entire byte array, rather. It then gets the actor ID. If it retrieves the actor ID, it sets the actor, or if it does not, it sets the actor to null. It then gets the component ID to invoke on. If the actor was found, it tells the actor to receive the state. So in this case, it's going to set the actor position and actor rotation, and then it's going to tell its inheritor to receive the full state. In this case, inside of our player avatar actor, we receive our ID, our max health, and our health. If the actor does not exist, we get the mapped component. We then tell our prefab factory to instantiate the mapped component type. We then tell the actor to initialize, then we tell it to receive state, and then we tell our actor repository that we've created an actor. Now, if we got a partial update, then we simply say receive state on all of the actors. A partial update will never result in creating an actor, because only full states can create actors. On actor destroyed, pretty straightforward. All it does is destroy an actor. On invoke method on actor. This is the method that's responsible for receiving the proxy events. It basically just retrieves the method out of the component map and invokes it against the deserialized arguments. So this is the exact same code that we already have seen time and time again with our client systems. It's just this time it's invoking on the actors. So how do we create actors? Well, there is, in our infrastructure, we have this actor behavior. All you have to do to create an actor is, assuming you have an interface. So let's say I wanted to create a creep. I would create an interface called iCreep as a component in my base project. I would then create a class here that inherits from actor behavior and implements iCreep. I would then write all the logic I want into this for that creep, for the client side. I would then go ahead and create a prefab and place it into prefab's actors that contains a script of that type. And that's it. Now, whenever the server requests that we create a particular actor of a particular type, it'll instantiate this prefab and position it for us. So that's pretty cool. Another interesting thing is the player avatar actor, you'll notice, is used for both our own avatar and the enemy's avatar. So how do we do that? Well, inside of our receive full state, what I do is I say if the ID of the avatar that was created is us, then we add a new component to it, our player controller. Couldn't be simpler. So we don't have to do any sort of thing where on the server where we tell something different about our actor versus other actors. All we have to do is send in all the information about all the avatars, and if it's us, then we attach our controller to it. If it's not, we just let it be controlled by the server. And then our player controller, super straightforward. It just uses a nav mesh agent. Alrighty. So the last thing I want to point out about the actor system are the different kinds of actors. So you won't see any other examples of anything but a transient actor yet, but there are different kinds of actors. None, which is invalid. Persistent actors mean IDs are set in stone and not auto-generated. So, for example, a persistent actor might be a object that saved the database and then reloaded. A transient actor is an actor that's just instantiated and has a new ID every time a actor is instantiated. So, for example, our avatars are transient actors. Creeps would be transient actors. Scene actors are actors that are constructed within Unity. And what I mean by that is, eventually what we're going to be able to do is I'm going to be able to pop open this Arena 1. I'm going to be able to come in here and place a tower right here. Place a big tower right here. Throw on a special component onto it to say, this is a scene actor of this type. Then the server, when we build the client, process out all of our scene actors and tell the server about them. So then when the server loads, it'll instantiate all the scene actors on itself. So scene actors are really cool because we can place them within Unity itself and configure them within Unity itself, but then the server has complete control over them. And then finally, we have server-side. That should be fairly straightforward. A server-side actor is an actor who's only on the server and has no client-side representation. So this actor would not inherit the actor type that accepts a proxy, because there would be no proxy. So an actor ID also is a use short combined with a kind. So it's 3 bytes, and you can have 16,000 actors per type, which should be more than enough for what we're doing here. Alrighty, so again, that took way longer than I thought it was going to, but I hope you guys got a good overview of the actor system, at least where we're going. You might want to, I guess, maybe watch this video once or twice, or maybe not. It's super long, and I apologize. But at the very least, this is what you just saw is effectively our roadmap for the next chapter. All of this stuff, plus an actual running game, will be implemented by the time chapter 12 ends. I'm still going to be developing on my R&D build. So my R&D branch will still be developing, and we'll still be doing playtest. So my R&D branch will be ahead of what we're doing on video. And that's really important for me too, because I want to see how this stuff kind of works before I spend time telling you guys, oh, hey, you should write this, you should write that, without me having tested it first. So I want to, within the next week or two, actually get the game running on my own R&D branch so that we can playtest it. So in that light, what we're going to be focusing on at first are the infrastructure changes. We're going to be creating our deferreds. We're going to be setting up our project structure a little bit better. You might notice we have a new MMO base.utilities. We're going to be doing a little bit work on our build system, and we're going to be doing some changes to our system components and all that fun stuff. But once we're done with all of that, then we'll move on to actually building out the actor system. Anyway, I hope you guys enjoyed that overview and have a good idea of where we're going from this point forward. And I guess we'll see you guys in the next video.